This video is going to be a bit different than my other videos. This video is here to help you practice your differentiation. So that being said, please approach it a little bit differently. Rather than just watching me differentiate, as I've done in the other videos, you should at some stage pause the video, try to find the derivatives yourselves, and then check with my explanations if you didn't get it right, or just check that you got it right. So I'm going to be working through examples. So the video itself is going to be longer, but it's going to contain a lot of examples to make sure that you can differentiate and you can test yourself. But it's better for you to pause, try it yourself, and then look, rather than just watching me differentiate. But if you just want to watch some more differentiation, here we go. Just a bit of background. By this stage, you should know the product, quotient, and chain rule for differentiation. You should know implicit differentiation. And here are all the differentiation rules and shortcuts that we are going to be using. I'm not going to use all of them, but at this stage, these are the ones you should know and the ones I assume you know. So let's jump right in and get started. So here's the first three functions. So it might be a good idea, whichever way you want to do it, but to pause, take down the function, try to differentiate, then watch me do it and check if you're on the right track. So let's see. The first one, we've got the quotient of two functions, sine of 6x divided by 4x squared minus 2x. So we know this is the quotient rule. So if I want the derivative, dy dx, we start at the bottom. It's the denominator squared. Square that denominator. Then write down the denominator times the derivative of the numerator. This is the quotient rule, so you need to know the quotient rule. What is the derivative of sine 6x? Well, it's cos 6x. And the chain rule tells me to multiply that by 6. I'm still busy with the quotient rule, minus the top, which is sine 6x, times the derivative of the bottom. I'm using the words top and bottom. It's the numerator and the denominator, but you know what I mean. So what's the derivative of the denominator? 8x minus 2. Now please remember to put those in brackets because it's more than one term. So there's the derivative. You can tidy it up a bit, change it around a bit, but you can, I'm just interested in the differentiation, so you can leave it there. Next one, we've got a function to the power 1 over 5. So the chain rule tells me if I've got a function to the power 1 over 5, the derivative is 1 over 5 times the function to the power 1 over 5 minus 1, so it's minus 4 over 5, times the derivative of the function. So what's my function? 3x squared minus 2, the derivative of which is 6x. Now, just for interest's sake, that can be written in a number of ways. My constant is 6 over 5. My numerator is 6, so I've got 6x over 5. Now, this whole bracket you can write as the fifth root of 3x squared minus 2 to the power 4. So that's a different way of writing the same thing. It's not incorrect, but it depends how you're presenting your answer. All right, let's look at the third one. G of x given there. Take a moment, try to differentiate it yourself, and then I'll do it. This is 3 terms, so we'll just differentiate each term because the derivative of the sum or difference between two terms is just the sum and difference between the derivatives. So cosec squared. Now for that you need to know what the derivative of cosec is, but before we look at the derivative of cosec, this is cosec squared. So it's a function squared. So the chain rule tells me the derivative of a function squared is 2 times that function to the power 1 times the derivative of the function. Now I'm looking at the derivative of cosec. So the derivative of cosec is minus cosec cot, but it's of 3x. So I've got minus cosec 3x cot of 3x. But another chain rule, because there's the 3x, I must still multiply it with the derivative of 3x, which is 3. So we have to apply the chain rule twice here. So it's a function squared, so the derivative is 2 times the function to the power 1 times the derivative of the function, which is what we did there. Now the rest of it. E to the power, we like that one. The derivative of e to the power is just e to that power. But because it's a function, the chain rule tells me I must multiply it with the derivative of the function, 10x minus 2. plus the derivative of 4 to the power x is 4 to the power x, ln 4. The next three, here we go, get ready. This first function is the product of two functions, so I'm using the product rule. So I've got the first times the derivative of the second. The derivative of the root of a function is 1 over 2 times the root of that function, times the derivative of the function, which is 2x, plus derivative of the first part, so we've got minus sine x minus e to the power x times the second, the root of x squared minus 1. All right, now this one can be represented in many different ways, so just be aware of that. You can simplify it by cancelling out 2's. You can put it on a common denominator of the root of x squared minus 1 if you want. There's lots of options, but that's the derivative. Next one, dy dx. Again, product rule. So t to the power 4 times, what is the derivative of a root is 1 over 2 times that root, times the derivative of whatever's inside, which is t plus 1, so that derivative is just 1, plus 4t cubed times the root of t plus 1. Now let me show you, when I said with the previous one you can put it over a common denominator. This is a technique that is sometimes used if I want to represent it in one term. I can write this as a common denominator of 2 root t plus 1. So the first part is fine. We've got t to the power 4. Now the question is, what's going on here with the second term? Because it's not actually over a root. But what you have to remember is if I've got the square root of a, I can write that as a divided by the square root of a. So that's what I'm going to do with the second term. So I'm going to say, now I've got to accommodate this 2 as well. So 2 times 4t cubed times, now I've got the a, which is t plus 1. So that's a different, and that can then be simplified as well. So you can write it as one term. This is not required necessarily, but it might be an option for an answer. All right, let's look at the next one. Ln of a function. Now when we're given ln of a function, hopefully you remember before I start differentiating, I use my logarithmic properties, logarithmic differentiation, to take this apart. So this is ln of the root of x plus 5. So it's ln of x plus 5 to the power of half. So that's a half ln of x plus 5 minus ln of x squared plus 3. And it's much easier to differentiate that function. So the derivative is now 1 over 2. So I'm just keeping the half there. What's the derivative of ln x plus 5 is 1 over x plus 5 times the derivative of x plus 5, which is just 1, minus 1 over x squared plus 3 times the derivative of x squared plus 3, which is 2x. Now, if you did not recognize that that is the easiest way to differentiate this function, and you used ln and the quotient rule, with a lot of algebraic manipulation, you'll get to the same answer. So you still get the same answer, it's just a longer route to get there. All right, next one. Again, a product rule. This looks similar to ones we've had before. The derivative is then equal to the first times the derivative of the second plus the derivative of the first, 1 over 2 root t minus 1, times the second. And there we go. Yet again, you can make it one term. Let me show you that technique again. Yet again, that's not always required, but sometimes you can represent the answer like this. This is going to be 2 root t minus 1. So yet again, if I've got the square root of a, I can write it as a over the square root of a. So here in my first term, I've got the root of t minus 1, but I can write that as t minus 1 over the root of t minus 1. But I must accommodate this 2, so it's 2 times that times 3t squared plus t cubed. And you can simplify that numerator from there if you want to make it even tighter and nicer. So I've got 6t cubed plus 1t cubed gives me then 7t cubed t squared minus 1, so it's minus 6t squared. There we go. So that's a much tidier answer, but these are all the same. So it depends how far you need to take it. All right, next one. Tan of sec of x. Let's take a look. It's tan of a function. I don't worry about the function, what it is now. It's just tan of a function. The derivative of tan of a function is sec squared of a function. Whatever the function is, I just rewrite it. Now, times the derivative of the function. What is the derivative of sec of x? The derivative of sec of x is sec times tan. So that's sec of x times tan of x. So don't get confused with all the sec of x's here. That's how it comes out. Next one. E to the power x times 3x squared plus 5x. Again, it's a product rule. So the derivative is the first times the derivative of the second, 6x plus 5, plus the derivative of the first times the second, which is 3x squared plus 5x. And yet again, if you want to tidy it up, you can take e to the power x out as a common factor, and you have 6x plus 5 plus 3x squared plus 5x. You can simplify even further, and you've got 3x squared plus 11x plus 5. So you can simplify it, you don't have to, but depending on which format you want your answer, those are all possible correct answers. All right. Now let's look at these next two questions. F and G, those two functions, they look a lot the same, but they're not the same. Number F, I can rewrite that as ln squared of x plus 2 over x squared minus 5. Where the second function is just ln of that whole fraction squared. So there's definitely a difference. Now, if I've got to find the derivative of a function square, that derivative, so this one I'm not going to use my logarithmic laws. I'm going to get the derivative first because I have to use the chain rule, and the square is what happens first. So the derivative of something square is 2 times that thing times the derivative of that thing. Now I've got the derivative of ln. Now there you can take it apart, or if you want to go do it by brute force, the derivative of ln of a function is 1 over the function x plus 2 over x squared minus 5 times the derivative of that function, which gives you the quotient rule, x squared minus 5 squared. Write it down, x squared minus 5 times the derivative of the numerator minus the numerator, x plus 2 times the derivative of the denominator, which is 2x. All right, that's a very ugly answer. We could have done it a little bit prettier, but there we go. Whereas the next one, I've got ln of a fraction square. So before I differentiate, I'm going to make this prettier. It's ln of something squared, so it's 2 ln of x plus 2. That square goes to the numerator and the denominator, minus 2 ln of x squared minus 5. Now I'm going to differentiate, and that derivative is then 2 over x plus 2 times the derivative of x plus 2, which is just 1, minus 2 over x squared minus 5 times the derivative of x squared minus 5, which is 2x. So these functions look similar, but they're totally different. All right, h of x. We've got a product again. The derivative with the product rule. First one times the derivative of the second. It's x cubed. The derivative of the root is 1 over 2 times that root times the derivative of the root. What's under the root? So that's 2x. Plus the derivative of x cubed, which is 3x squared, times the root of x squared minus 5. All right, here's the next three. Take a moment, try them yourself, and then see how it goes. This first one here, we've got the quotient, so a fraction, one function divided by another. So we're going to use the quotient rule, and the derivative dy dx is going to be equal to the denominator squared, 2x minus 1 squared. Write down the denominator, take the derivative of the numerator, which is minus 4. Put it in brackets because a multiplication sign and a minus sign next to each other is just very clumsy. Minus the numerator, minus 4x plus 1, times the derivative of the denominator, which is 2. Now, This is all linear functions, so you can simplify that numerator to make it look much prettier. But I'm just focusing on the differentiation, but you should be able to make that look a bit better. Again, ln of a function. Now we're getting to, remember, we've got to take it apart first before we differentiate it. Ln of a function to the power of half. So that's a half ln of the numerator, 3x plus 1, minus the half went to the denominator as well, a half ln of x to the power 2 plus 5. Much easier to differentiate at this stage. So the derivative is 1 over 2 times 3x plus 1. So it's 1 over 3x plus 1 times the derivative of 3x plus 1, which is 3, minus the half just tags along. The derivative of ln of a function is 1 over that function, x squared plus 5, times the derivative of the function, which is 2x. Gx, again, we can take it apart first. So this is ln of 2x plus 1 minus a half ln of x squared plus 5. Just notice the difference between this example and the previous one. The previous one, the root was over the whole quotient. This one, the root is only in the denominator. But when I differentiate, we're using the same techniques. Ln of a function, so it's 1 over that function, 2x plus 1, times the derivative of the function, which is 2, minus, that half tags along, derivative of ln of a function is 1 over that function, times the derivative of the function. And then you can see in the second term the 2's can cancel out if you simplify it. All right, some more to look at. What about ln of arcsine of x? So the derivative of that, derivative of ln of a function is 1 over the function. So 1 over arcsine of x times the derivative of the function. What's the derivative of arcsine of x? Hopefully you remember that. 1 over the root of 1 minus x squared. What about tan of cos x? The derivative of tan of a function is sec squared of a function, whatever that function is, times the derivative of the function. Remember to put it in brackets because of that minus sign. 4 to the power times ln, so again, first the product rule. So the derivative, we start with the product rule, so it's the first one, times the derivative of the second. The derivative of ln of something is 1 over that function times the derivative of that function, which is 6x, plus the derivative of the first part, so the derivative of 4 to the power function is 4 to the power function ln 4 times the derivative of the function, which is minus sine x, multiplied by the second part, which is ln of 3x squared. The root of arctan, the derivative of the root of arctan, is then 1 over 2 times the root of arctan x times the derivative of arctan, which is 1 over 1 plus x squared. All right, these are lots of examples. If you can do them all, then your differentiation is looking good. All right, let's just look at some applications. Find the slope of a tangent line to a curve at a point. All right, so I want a slope of a tangent line, so we know we're looking for derivatives. So let's find the derivative first of this function, dy dx. Product rule. First one times the derivative of the second, plus the derivative of the first times the second. Now I'm just going to tidy this up. This is minus x times sine x plus cos x. And we're looking where x is equal to pi. Remember, when we're talking about calculus, we're talking about radian measure. So x is equal to pi. If I substitute that in there, now you can use a calculator. I like to just look at the graph. That's sine, there's pi. So sine of pi is 0. So that's minus pi times 0. And cos, that's cos, there's pi. Cos of pi is minus 1. So that is equal to minus pi times 0 times minus 1. So that's minus 1. Right, let me just rewrite this before saying that's minus 1. My gradient of my tangent slope, my gradient, we often use m for that, is dy dx at the point where x is equal to pi. So let me just make the notation a bit better. So that is minus 0 plus minus 1, and that is minus 1. Next one, I've got x over sine x And now we're looking at x equal to pi over 2. So let's look at our derivative firstly. Quotient rule. Sine squared x. Sine of x times the derivative of the top, which is 1, minus the top times the derivative of sine of x, which is cos x. So our slope is the derivative where x is equal to pi over 2. So let's take a look. We've got pi over 2 is over here. Sine of pi over 2 is 1. So that's 1 minus x is pi over 2. Cos of pi over 2 is 0. Sine of pi over 2 is 1 squared. So it is 1. That's the slope of the tangent line to the curve. All right, so let's just practice our implicit differentiation to round this off. Remember, implicit differentiation is where the chain rule comes into play. So every y here is a function of x, so we need to treat it such and remember to use the chain rule. So let's take a look. We're differentiating both sides. E to the power y, so e to the power of function of x, the derivative is e to the power of function of x times the derivative of the function. For x squared, that derivative is just 8x. Plus sine y, the derivative of sine of a function, is cos of the function times the derivative of the function. On the right-hand side, x times y, so the product rule. X times the derivative of y, which is just dy dx, plus the derivative of x is 1 times y. Now we need to sort this out and get dy dx alone on one side. So here I've got an e to the power y times dy dx. The 8x I'm taking to this side, and I've got a cos y dy dx minus, here's a dy dx, I want it on this side, x times dy dx. And the plus y stays there. So you can take dy dx out as a common factor, and you've got e to the power y plus cos y minus x is minus 8x plus y. So this is just algebraic manipulation. This first step is the most important, that you get your derivative right. So dy dx is then equal to minus 8x plus y over e to the y plus cos y minus x. And the last one, some more implicit differentiation, just to practice it again. Cosec of a function of x. So the derivative of cosec is minus cosec cot. So this is going to be minus cosec y cot y times the derivative of y, which is dy dx. Minus, we've got ln of x, so it's just 1 over x. On the right-hand side, I've got a product, 2x squared times y. So it's 2x squared times the derivative of y, which is just 1 dy dx, plus the derivative of 2x squared, which is 4x times y. So yet again, all the dy dx is on one side, take it out as a common factor. On the right-hand side, what's left? So I've got a 4xy, the minus 1 over x becomes plus 1 over x. And on the left-hand side, if I take out dy dx as a common factor, I've got minus cosec y cot y minus 2x squared. So dy dx is equal to 4xy plus 1 over x over minus cosec y cot y minus 2x squared. So hopefully by now you're getting all of these right, and you can now differentiate all these functions that we have looked at.